One of the greatest challenges in astronomy has been to find the first generation of stars born in the universe. According to our current cosmological models, these stars formed just 100 million years after the Big Bang, when the universe was less than 1% of its age. The search for the elusive celestial bodies has returned empty-handed time and time again. But now, a team of astronomers has made a groundbreaking discovery, providing concrete evidence of the traces of the first stars formed in the universe. So how did the astronomers identify the first generation of stars? What clues did they use to differentiate them from the countless others that litter the night sky? Finally, and most importantly, why is this discovery so important in physics and astronomy? Before jumping into the discovery, let's have a look at the gravity of the situation. According to the European Space Agency, there are an estimated trillion stars in the observable universe, a number so large it's difficult to comprehend. Carl Sagan once wrote that there are more stars in the universe than grains of sand on Earth, and recent estimates suggest that for every grain of sand on our planet, there are a staggering 10,000 stars in the universe. So how is it even possible to find out the very first stars or their remnants in the universe? The answer is chemistry. According to the Big Bang Theory, primordial nucleosynthesis began when the universe was 3 seconds old. It lasted for 20 minutes. In this brief period, nuclei of only 2 major chemical elements were created: hydrogen and helium. It was only 100 million years later that the first generation of stars, called population 3 stars, were formed from these 2 elements. These stars were massive, and they rapidly fused hydrogen and helium into heavier elements in their core. For the sake of simplicity, in astronomy, every chemical element other than hydrogen and helium is referred to as metal. So population 3 stars fused metals such as carbon, oxygen, neon, iron, among others in their cores. When these stars underwent supernova explosions, they enriched the interstellar medium with these heavier elements. From this enriched medium, the subsequent generation of stars, called population 2 stars, formed. They already had a relatively higher concentration of heavy chemical elements. Finally, the death of these stars gave birth to metal-rich population 1 stars. The Sun is a prime example of a population 1 star. So this gives us an idea of what to look for. The first generation of stars, or the population 3 stars, are extremely old, just a fraction of years younger than the universe itself. They also lack heavy chemical elements and are metal-poor in nature. Also, they formed when the universe was denser and almost 30 times hotter than it is today. As a result, they must have burned incredibly hot and bright, being up to 100 times more massive than our own Sun. Despite having a clear picture of what these stars might look like, astronomers have yet to observe any of them. There are 2 reasons for this. Firstly, most population 3 stars have already lived out their lives, burning through their nuclear fuel in just a few million years, and ending their lives in spectacular supernovae. Secondly, even if these stars still exist, they are incredibly dim and difficult to observe using our current technology. The only way we can hope to catch a glimpse of them, or their remnants, is through gravitational lensing. Because of lensing, background objects can get highly magnified. This gives us a glimpse of objects that would otherwise remain out of view given our current technology. One such discovery came when the Hubble Space Telescope observed Earendel, the most distant single star ever discovered in the universe. Although it seems impossible to spot the first generation of stars, at least there's a way we can find their traces littered in the universe. And for this, we need to study supernovae. In a Type 2 supernova, A massive star typically leaves behind a dense remnant, such as a neutron star or black hole. However, first-generation stars can have a different fate. When they explode in a supernova, they can blast everything outwards in an ever-expanding cloud, leaving no stellar remnant behind. This type of explosion is known as a pair-instability supernova, which is a theoretical type of supernova only possible in the most massive stars. It is believed that such supernovae from first-generation stars may have played a crucial role in seeding the ancient interstellar space with heavy elements, which were later used in the formation of planets like Earth, allowing the emergence of life as we know it. For astronomers studying population 3 stars, the remnants of these explosions could be a vital tool to learn more about these ancient stars. However, light from such mega explosions has likely faded into the distance over time, leaving us with just a diffuse cloud containing a complex mix of elements to investigate. Nevertheless, even such a cloud can reveal a wealth of information, as has been demonstrated in previous studies. By analyzing the chemical composition of such clouds, astronomers can infer the processes that produce the elements and gain insights into the early universe's conditions. Therefore, while direct observations of first-generation stars may be impossible, the remnants of their explosions offer a unique window into the universe's early history, and the similar approach was used in the recent discovery. Astronomers using the 8.1-meter Gemini North Telescope in Hawaii recently made an unusual discovery while analyzing the second most distant quasar detected so far. This quasar also contains the second most remote and oldest known supermassive black hole, with a reported redshift of 7.54. To study the region surrounding this quasar, the researchers used the Gemini near-infrared spectrograph, which splits the light emitted by celestial objects into constituent wavelengths that carry specific information about the elements present. Gemini is one of the few telescopes of its size with the necessary equipment to perform such observations on Earth. To analyze the spectrographic data from the clouds surrounding the quasar, the team used a chemical abundance estimation method based on the observed ultraviolet flux. This method is also sensitive enough to measure a conspicuously low magnesium to iron ratio. Although originally developed for quasars at a redshift of up to 3, the team advanced it to its required redshift value of 7.54. Their analysis revealed that the material surrounding the quasar contained over 10 times more iron than magnesium compared to the ratio of these elements found in the Sun. Moreover, the iron abundance itself was a factor of 20, larger relative to the solar iron abundance. These findings provide important insights into the early universe's chemical evolution, suggesting that the universe's first stars were likely responsible for producing large amounts of heavy elements like iron. The ratio of iron to magnesium was much higher than what would be expected from typical supernovae, challenging the standard view of chemical evolution. However, this ratio could be explained by the debris produced by an all-consuming explosion of a massive first-generation star with a mass between 150 to 300 solar masses. In other words, only a pair-instability supernova is known to create such debris, which means that we have actually found the leftover of a population 3 star belonging to the exotic first generation of stars that formed in the early universe. This finding provides intriguing evidence of first-generation stars and has the potential to shed light on the evolution of matter in the universe. As stars age, they can provide important clues about the universe's origins and evolution. The James Webb Space Telescope's advanced capabilities will enable astronomers to study even the most distant and ancient objects in the universe. By analyzing the chemical composition of these objects, researchers can better understand the conditions that prevailed during the universe's early history and how it has evolved over time. Recently, astronomers discovered a dazzling comet approaching us. It may outshine some of the brightest stars in the night sky when it passes by our planet. If you missed this episode, be sure to catch up on this exciting discovery.